Hey everybody, welcome back to another video on Feynman integration. Today we'll be evaluating this integral right here, integral from 0 to pi over 2 of e to the negative tangent x minus e to the negative 2 tangent x all over sine of 2x dx. And like always, we'll create a function of t closely resembling our original integral. In this case, I just put a t right in front of that tangent x right there, and that will give us a function of t. You'll notice that if you plug in if you plug in 2 into our function of t, you will get 0 because there will be a 2 there, making that e to the negative 2 tangent, e to the negative 2 times the tangent of x minus the same. So that'll give you 0. And also you'll notice that if you plug in 1, you'll get our original integral. So differentiating both sides of this equation will give us that f prime of t is equal to negative 1/2 the integral from 0 to pi over 2 of e to the negative t tangent x times the secant squared of x dx. And I'm sure you can all handle that derivative. The only thing is you might need to know that sine 2x is equal to 2 sine x cosine x. And now that I've given you that hint, doing that derivative with respect to t should be no problem. And then after that, we make the substitution where u is equal to tangent x. Subbing in, we get that f prime of t is equal to negative 1/2 times the integral from 0 to infinity. Again, our bounds of integration would change due to that substitution. Anyway, f prime of t is equal to negative 1/2 the integral from 0 to infinity now of e to the negative tu du, which if you evaluate that one, it's a pretty easy one. You'll get negative 1 over 2t. Integrating both sides of that will give that f of t is equal to negative 1/2 the natural log of t plus a constant of integration. Using the fact that f of 2 is equal to 0 will give us a value for c of 1/2 natural log 2. Plugging this in for c right there will give us our final expression for f of t. And then if we plug in 1 to find I, this will just cancel out because you'll be left with a natural log of 1 there. So this whole term right there would cancel out, leaving us with f of 1, which is equal to I, is equal to 1/2 natural log of 2, and that's written right there, and that's the answer. So some of you may have noticed that this integral seems a little bit too convenient, and you're right. I specifically developed this problem to work very nicely with Feynman integration. I didn't copy it out of a book or off the internet or anything. You might find it somewhere else, but I did actually come up with this integral on my own. And like I said, I made it up specifically to work really nicely with this technique. But I'm sure you can all agree that evaluating that integral with any other technique would be a nightmare. The only other way I can think of that would work would be contour integration. And you've got trig functions in the exponent, so I mean, you might be able to do it. I didn't try to do it, and I also didn't actually try to come up with an antiderivative to that, although I highly doubt one exists, at least not an elementary antiderivative. So that's off the table. Maybe you could do it with contour integration. I'm not sure, but this way works, and that's the way I recommend. Hope you enjoyed that.